Okay, so this is a little bonus section that we're going to cover in Chapter 8, and essentially it's just going to provide you another strategy for working with limits. And it's not something that we really could have introduced earlier in the class because this new strategy actually makes use of taking derivatives. And so it just speaks to the fact that here is another application of derivatives. It actually allows us to just evaluate more limits. And so the rule is this. It's called L'Hopital's rule. And what I'll do is I'll just kind of walk you through it, and then we'll look at a few examples, and I'll try to informally talk about maybe why this works. So the rule is this. Let f and g be functions that are differentiable on an open interval ab containing some value c, except possibly at c itself. Assume that the derivative is not equal to 0 for all x in the open interval, except possibly at c. If the limit of f of x divided by g of x as x approaches c produces an indeterminate form, so like if you're doing the limit of f divided by g as x approaches c and you get an indeterminate form, then we can solve that limit by solving the corresponding, this limit right here, this limit of f prime of x over g prime of x as x goes to c, provided the limit on the right exists or is infinite. This result also applies when the limit of f divided by g as x approaches c produces any one of the indeterminate forms. And so basically L'Hopital's rule takes care of indeterminate forms. And remember, we've learned strategies in the past for doing limits of indeterminate forms. We've talked about the cancellation technique or the rationalizing technique, or what else? We've had embedded fractions, things like that. But now when we get 0 divided by 0, or infinity divided by infinity, or negative infinity divided by negative infinity, or there's even other indeterminate forms also. There's 0 to the 0, you could see that sometimes, or 1 to the infinity, things like that. All of these indeterminate forms you can solve using L'Hopital's rule. We're actually going to focus on a lot of 0 divided by 0 forms, as well as infinity divided by infinity. So I'm going to go through these few examples and refer to this as you're completing some of the questions on the homework for L'Hopital's. You'll also see just a couple of these basic types of problems appear on your test. So example 1, the limit of sine of x over x as x goes to 0. Now we already know what that's equal to. That's a special trig limit that we saw earlier in the class. This is equal to 1, and we could look at that graphically, we could look at it numerically, but notice here that if we substitute 0 in, you get the sine of 0 divided by 0, and the sine of 0 itself is 0, and so this is an indeterminate form. So according to L'Hopital's rule, what we can say is the limit of sine of x over x as x goes to 0 is equivalent to the limit of the derivative of sine of x over the derivative of x as x goes to 0. So I'm doing cosine of x all over 1. Now you should know here that we are not doing a quotient rule. This is not a derivative of a quotient. This is the derivative of the numerator over the derivative of the denominator. So that's why this is also probably a good time to introduce this rule, because it's not going to confuse you with how to actually do the derivative of a quotient when we need to do that, but we're not doing that here. And so now when we apply this rule, I guess the question is, can you solve this? Can you evaluate this? And this is a new limit question. Well, let's do a direct substitution. And you do a direct substitution, you get the cosine of 0 is equal to 1. So if you get 1 over 1, then our answer ends up just being 1. And it's actually a really simple process sometimes. You're going to see some differences and some challenges in some of these other examples as we go through this, but it is a pretty simple process. I would encourage you to check out the proof of this in Appendix A. When we look at another one of these examples in just a minute, I'll kind of talk you through how I sometimes informally think about why this works. It basically boils down to exactly what the theorem suggests, and that is, or the rule suggests, and that is that when we get an indeterminate form, something like we have here where it's 0 divided by 0, if we know that the numerator is going to be 0 and the denominator is both going to be 0, let's see what gets to 0 the fastest. And so basically, what's the rate of change at 0, and what's the rate of change at 0 for the denominator? And depending on what's getting to that 0 faster, that's kind of the idea of of what's happening behind the scenes here. So all right, so look at example 2. If you look at example 2, we've got limit of 1 minus cosine of x over x squared as x goes to 0. So a direct substitution would reveal 1 minus the cosine of 0. So that's going to be 1 minus 1 all over 0 squared. So you end up with 0 divided by 0. Okay. This is actually quite similar to an example that we saw earlier in the class. It was the limit of 1 minus cosine of x over x as x goes to 0. That's equal to 0. It's a little bit different though. So according to L'Hopital's rule, this is going to be, this is equivalent to the limit as x goes to 0 of the derivative of 1 is 0. The derivative of negative cosine of x is actually going to be positive sine of x, since the derivative of cosine is negative sine. And the derivative of x squared ends up being 2x. And so we go to take a derivative, or I'm sorry, we go to evaluate this here through direct substitution. You look at that and you see that's the sine of 0 all over 2 times 0, but the sine of 0 is 0, so you actually get 0 divided by 0 again. Well, guess what you could do? You have an indeterminate form. You can apply L'Hopital's rule. So this is equal to limit as x goes to 0. I'm going to do the derivative of sine of x again, and that's now cosine of x all over the derivative of 2x, which is 2. And so in this case, you can see that if we do a direct substitution and you plug 0 in, you end up getting the cosine of 0, which is 1, and that's all over 2. So the limit in this problem is equal to 1/2. And so, and this is a great example of how you can actually apply L'Hopital's rule 2 different times, 2 times in a row. But you've got to make sure before you just start applying that rule that you do in fact have that indeterminate form again. Okay, let's take a look at example 3. And so in example 3, we've got the limit of e to the x over x squared as x goes to infinity this time. So if you did a direct substitution with infinity, and remember, it's just think of infinity as a really big number, you end up getting another indeterminate form because it's going to be essentially infinity divided by infinity. So the big question is, when you're looking at this, it's like, so is my answer going to be infinite? Is my answer going to be 1? Is my answer going to be 0? And a lot has to do with how fast the numerator and the denominator get to infinity. And so that's, again, why this is how I justify to myself why I can apply L'Hopital's rule and answer this limit question by looking at basically the rate at which my numerator is going to infinity and the rate at which that denominator is going to infinity. So I end up doing the limit as x goes to infinity of the derivative of the numerator over the derivative of that denominator. And if we do a direct substitution, you can see that we end up with e to the infinity all over 2 times infinity. So we again have that indeterminate form. So let's apply the L'Hopital's rule again. So we end up with limit as x goes to infinity of e to the x all over 2, because I'm doing the derivative of my numerator over the derivative of the denominator. And you can see that this leads you to e to the infinity all over 2, and so you could justify your answer ends up being infinite here. And so essentially this e to the x ended up converging to infinity much faster than what the x squared did. And as a result, as x got bigger, the limit of this ratio ends up being infinite. So again, I think that just by thinking a little bit about this, you can justify why L'Hopital's rule might work, why you can answer a limit of a ratio by looking at the limit of the ratio of the derivatives of those functions. Okay, one more example, example 4. And in this one, we have the limit of, let me get this cursor out of there. So we've got the limit of x squared all over e to the x minus 1 as x goes to 0. So again, direct substitution. And when you do your direct substitution, you get 0 divided by 0 again. And so L'Hopital's rule applies, and we can say that this is equal to the limit of 2x all over e to the x as x goes to 0. And if you do a direct substitution here, you end up with 0 divided by e to the 0, and e to the 0 is actually 1, so you do not have another example of where L'Hopital's rule could be applied again. This is not an indeterminate form. This would suggest our answer is 0. And again, I think the way that I rationalize why this works is I say my numerator and denominator both end up going to 0 as x goes to 0, but it looks like the numerator ends up going to 0 potentially a little bit faster than what that denominator is going to 0. And so that's how I justify, again, why I can do the limit of one function divided by another function by doing the limit of the derivative of that first numerator divided by that first denominator. Okay, so hopefully this gives you enough. I know it's just a few examples, but it's a pretty I'm going to keep it pretty simple here. We're not going to be looking at a lot of the complex indeterminate forms. So hopefully this gives you enough to complete the homework and apply this concept when you see it in the future.